what we've covered this far is when we don't know the mean within our population, a handy method we can take is to take a sample. And once we've taken that sample, it's as simple as making a best guess with our sample mean, and then building in some level of uncertainty through a confidence interval. And so far, what we've done is use the z-distribution with the population standard deviation, and of course the sample size. And that's really the system we've used thus far, right? And we've had to make the decision of, do we want 95% or 90% and so on. Now, when we, in reality, or in what is most often the case, is not only do we not know the population mean, we also don't know the population standard deviation. Okay, and again, because to think of the scenario where we would know the spread or the standard deviation within the population but not know the mean, there'd be very few of those actual cases. So what do we do when we don't have the standard deviation, and really where does this create issues in our previous example? Well, we can still take the sample, right? Nothing's wrong there. Where we start to get in trouble is if we notice up in our top example, we obviously have an issue because we are using directly the standard deviation, the population standard deviation here. We also are going to run into an issue when we use the z-distribution. Okay, so there's two big things that need to change when we don't know the population standard deviation. Obviously, we have to address sigma showing up, and we also will have to do something with the z-distribution. So first, let's talk about sigma itself. So what do we do with the fact that sigma shows up in our confidence interval? Well, when we take our sample, we of course can get an estimate of the sample, we get an estimate of the population mean. We also get an estimate of the standard deviation. And if you recall back to maybe even chapter 1, we talked about sampling versus population, and we know that S is the sample standard deviation, right? And sigma is the population standard deviation, just abbreviate SD. And so we can use S as a good estimator of sigma. And so that's what we're going to do here. And in fact, we're just going to plop it in there to the equation. Okay, so we're roughly saying, hey, S is a pretty good approximation. It's roughly equal to sigma, or we have a sense that it's approximately the same. And so we're going to plug it in. And so our process is then we're still going to use x bar as our best guess for mu. Our confidence interval now includes S. We'll still use square root of n here to accommodate the sample size. Now, the z-score, remember the z-score itself, or the z-table, the z-distribution more precisely, the z-distribution is based on a standard deviation, right? So it's all about recall back taking different distributions and associating them with this standard normal distribution with a mean of 0 and a standard deviation of 1. Okay, and so we're running into some issues with using that directly, but also we want to take note of so this S that we've used here. It's a good approximation, or it's a good estimate of sigma, but it's not exact. Okay, so just like x bar, we know x bar is not an exact, not exactly equal to mu. Right, our sample mean is not going to be the population mean. We're going to have some sampling error, and that's why we're building this confidence interval. In a similar sense, we know we are guessing. We think it's a good guess. We think the population standard deviation is around S, but we don't know, and we can't expect it to be exactly right. And so to build in, you can think of it as an extra layer of uncertainty. we're going to, instead of using the Z distribution, we're going to use what's called the T distribution. Okay, so that's the other big change. When we don't know the population standard deviation, we have to make two adjustments. Number one, we put in the sample standard deviation in place of the population standard deviation, and we use the T distribution instead of the Z distribution. Other than that, the process is the same. Okay, and we'll dig deeper into the T distribution and how we play around with the T table instead of the Z table in a future video. But let me first just kind of give you a broad overview of the T distribution. Now, the T distribution is really the T distributions. It's a family of distributions, much like, remember we talked normal distributions as a whole family of distributions. The T distribution is very closely related, or again, I misspoke, the T distributions are all related to the Z distribution, but they changed, or which distribution we use is dependent on the sample size. Okay, so the process through which we decide, so we're still going to need to decide if we want 90 or 95%. We're going to look that up on a slightly different table than the Z table. We're not going to look it up on the Z table. We're going to use the T table. Now, the T distributions are a whole family of distributions, some fatter and some skinnier than the others. Okay, so depending on the sample size, we have a different shape of the T distribution. Maybe I'll change colors here just so they show up. Not that color. Just so they show up a little bit better here. Okay, so we can have all kinds of, I'm trying to draw that in the middle. We can have all different, many different T distributions here. Okay, and each of these is associated with a different sample size. So how we pick which samples, or how we pick which T distribution is based on our sample size. So for instance, this blue one might be n equals 18. And I shouldn't have done them both in yellow, but maybe this top one is n equals 30. Okay, and they get, and the other one would be a lower, so maybe the fatter one is n equals 6. Okay, I'm just kind of making those numbers up, but the point here is with a lower sample size, we have a fatter distribution. And that you can think of as building in extra uncertainty, right? So the smaller the sample size, the less certain we are about this kind of concept that, yeah, S is going to be close to sigma, right? We still, it's going to be a good estimator. It's a unbiased estimator. It works, but there's more uncertainty, and especially with only a few, in our sample size. So if we're only sampling 6 people, we have we're less sure about where sigma actually is. So we build it with a little more uncertainty. So we'll see how these numbers match up when we turn and look at the T table. But in general, the T, for a 95% confidence interval, the T number that we plug in is going to be larger than that Z value. Okay, so depending on the sample size, but with a Z, remember the Z up here is probably starting to memorize this, is 1.96. We, depending on the sample size, might be plugging in 2.3 or 2.1, or it can even be larger. It could be 3.8, depending on how large our sample size is. So on a small sample size, it might be something like 3.8. As we get closer and closer, or higher and higher in sample size, it's going to get closer and closer to that 1.96. And in fact, once you have a sample size of roughly over 200, the T distribution looks almost identical to the Z distribution. Okay, keeps getting, so basically one way to think about it is that the Z distribution is skinnier than any of these T distributions, but as the sample size of the sample size gets larger, that T distribution gets closer and closer to a Z distribution. Okay, so this might be the Z, and if we had an N of close to 200, it'd be pretty close to that red distribution. So we'll be back at looking at specifically how we calculate it, but hopefully that gives you some insight into the two big changes that happen when we don't know the standard deviation, as well as we don't know the population mean.